let's say, one instruction at a time, and a complicated one that does 10 instructions at a time. It's 100 times more complicated, right? And from what's the best way to do lots of instructions, complicated computers are not efficient. But there's so many applications where people care how fast it is. So when you're like clicking on your web page, you want that to come up as fast as possible. So the part of it's that's, let's say, what's it called? The logic of the web page. It's probably a serial narrative written by a human being. So you run that on a complicated computer that does it out of order and predicts what to do as fast as possible. But when you render the screen itself, that runs on large numbers of simple computers to make all the pixels. Right. And then there's a third kind of computer, which we're starting to invent, which is AI computers.
And that's what you're working on now?
Yes.
For TENS torrent?
Yeah. And there's a really good talk by Andrej Karpathy called Software 2.0. So all the first two kinds of computers, simple computers and complex out of order computers, they're running programs written by humans, right? And if you look at the code, it's literally declarative statements about operations and where to go, and it's serial. It's a linear narrative. Yeah, the different thing about AI computers is you use data to train the weights in neural networks to get you the desired result. So instead of the programs are no longer written by humans. Now, it turns out there's components of the AI stack that are written by humans, but at a high level, you use data to train it. So you have a big neural network and you want to detect cats. So you put a cat picture into the network when you start training, and the output is gibberish. And you compare gibberish to what a cat is, and you calculate the difference in what the network said versus the desired result, which is the word cat. And then they do something called backpropagation, which is mathematically sophisticated, but essentially take the error and partition it across the layers of the network such that you've sort of bumped each neuron a little closer to saying cat next time by taking the big error at the end and distributing it across. That's called backpropagation. And then you put another cat in, and if you have the right size network and the right training methods, after you show the network 1 million cats, and you put a cat in, it reliably says cat. And when you put a picture that's not a cat, it reliably says not a cat, right? And you never wrote any code that said anything to do with cats.
And can you understand what it is that the computer is doing now that it's recognizing cats?
A little bit. So people for years worked on visual computing, and they were trying to detect things like cats, right? And cats have a whole bunch of artifacts. They have round eyes, they have pointy ears, they have fluffy hair. So you could detect, it was called feature detection.
Mm-hmm.
So you would say, this will be a cat if I see the following colors, the following amount of fluffiness, the following number, 2 pointy ears, not 3, 1 or 2 round eyes, depending on the view, right? So you could write code, and the problem with that is, well, now the cat has an arbitrary orientation. So you do your feature detect on the picture, and the features have to search the whole image, and you have to rotate around, and it's sort of, and every single thing you want to detect, you have to write a unique program for. So you're done with cats, now you go to dogs. And then what about the dog that has slightly pointy ears? These dogs have round ears and cats have pointy ears. So it was sort of endless thing. And
right.
Same thing with speech.
Endless detail by detail construction.
Yeah. Like I had a friend who worked on speech recognition years ago. So you break speech into, the phonemes, so you can see those, and then they have frequency characteristics, and you can differentiate vowels from consonants. So the people working on speech were doing a whole bunch of analysis of analog waveforms of sound. And they were making some progress, but it never really worked. And then they trained neural networks you put the word in, and you have what's called supervised learning. So you play at language where you know what all the words are, and you keep telling the network how to correct. And with like 1 billion samples and a big enough neural network, it can recognize speech just fine. And if you train it with a broad variety of accents, it can work across accents. And then it turns out the bigger they made these networks, the more information they could put in. And then on the cat one specifically, they found, so when they first had a neural network crack the cat problem, I forget, it was like 50 layers deep. And if you looked in the layers, you could see that it was detecting pointy ears and eyes, but it was also detecting a lot of other things. And some things we don't know.
Yeah, well, if we see the back end of a cat walking away, we still know it's a cat, and it pretty much lacks eyes and pointy ears from that perspective.
The funny thing, if you take an object, like in light, right, you take a phone, you can project the phone onto a flat surface. Say that's a projection, right? And as you move it around, you get different.
It's a shadow.
Like, but think of it as a projection, right? So that's a projection of a light source on a flat plane. It's a fairly simple projection. But what if you had a light shaped like a cat and you shined that on the phone? What would the projection look like? And it turns out mathematically, there's an arbitrary number of projections. You can, like, we think of projections in 3 dimensions because we're 3-dimensional creatures, right? But there can be lots of projections. And then you can have the projection project on another plane. So that the neural networks are doing is they're teasing out all the details of what that is. And some of the projection planes give you what's called, size invariance or rotation variance. Like you could recognize a cat no matter which way it's pointing. Like your brain is a little specialized, like faces.
Right, it likes them to be vertical.
Right side up.
Yeah.
But with a little bit of work, you can recognize an upside down face pretty well, unless you have a problem.
Okay, so we could do 2 things here. We could either talk about let's go into you were an engineer and then you were a manager. And you've worked in lots of companies, some of which were incredibly creative, some of which were thriving to an incredible degree, and some of which were collapsing and irreparable. So what have you learned about what makes companies work? And more importantly, what have you learned about what makes them not work? And maybe what do you do then? Sure.
Well, that's a fun question. Well, first of all, I've noticed, and many people have noticed, this is not just me, that people, in engineering